So we're going to collect data for the iron thiocyanate lab given by Flynn, and we have our reference solutions here and our test solutions here, and we're going to make a Beer's law graph here. I'm using the Vernier Go Direct Visible Spectrophotometer, and really important part of this lab, as any spectrophotometry, we want to essentially set the spectrophotometer to look for a particular wavelength that this particular chemical, this colored chemical, that has a color, of course, because it's absorbing part of the visible spectrum of light. So we want to set the spectrophotometer with this color best absorbs. So I have just calibrated the spectrophotometer with an empty cuvette. I'm going to take that out. And by the way, I'm using Vernier's spectral program here for the spectrophotometers, and I'm going to put in one of the darker solutions of my reference solutions, and I'm going to see where the visible spectrum is best being absorbed. And we can see that little absorption spectrum here. And so I'm going to try to type in here best that I can, although I see a little number here. Yeah, so I'm going to try to move this slider over to best see. It looks like 452 is the peak absorbance here. So we're going to set the spectrophotometer to peak absorbance. I'm going to type, or I already have 450 there done. Okay, it already set that for me. So very important to understand that we're going to set the spectrophotometer to look at peak absorbance. And so we'll do that there. Okay, so now what we're going to do here is build a Beer's law graph. Okay, I'm going to take out the fifth reference solution, and I'm going to build my Beer's law graph from the reference known solution. So we've already mixed the solutions, we've already determined the molarity, and we're going to do that right now. So very quickly, I'm going to take my reference solution 1, and I'm going to read that absorbance, let that settle, and I'm going to hit collect. All right, and I'm going to tell keep because the computer doesn't know the concentration, and this is going to be 0.00. Oh, I got to make sure I'm on there. So I'm going to. So this molarity that we calculated through the lab is 0.00004. We're going to keep that point. All right, and then I'm going to move on and do the other reference solutions with the known molarities. Always wait to give it some time, and this next reference solution is, of course, a little more concentrated, so the absorbance goes up, so we know we're doing something right here. That's always a good sign. 0.00006. Again, we got these molarities by doing a dilution formula, MV equals MV, because we poured solutions together to set up these reference solutions, which, by the way, represent completion reactions because the amount of iron ions is about 1,000 times larger than the thiocyanate ions. Okay, so these are not at equilibrium, but we're going to use their actual known molarities to build a relationship that we're going to use to know when we are at equilibrium for the test solutions. In any case, I'm going to say keep. This concentration here is 0.00008, very dilute. Keep that point. And you can see we're somewhat making we should be making a pretty good straight line here. We're going to do a best fit line just to make sure. And we're going to take the fourth test solution. All right, give that a second for it to pick up. And we're going to keep that. And this is going to be a little more concentrated. So 0.0000, oh, this is 0.00010, okay? And then the fifth one, which is a little bit, okay, so we're going to keep this, and this one is 0.00012. Okay. All right, so not the greatest straight line, but we're going to use those relationships to build the best line. It looks like my outlier might be that fifth one, but we're going to still build the best fit line here. So I'm just going to get my apply curve fit, linear, and apply. Okay, and this is important because I'm going to use the y equals mx plus p to actually solve for the molarity of our actual test solutions that are going to be at equilibrium using y equals mx plus b. All right, so let's go just run the test solutions, okay, while my spectrophotometer is actually calibrated, okay, and let's do that right now, and we're going to write these down into our lab, okay, and when I bring the lab up, I'll have these values. So this is going to be test solution 6, and that's 0.116. That's the absorbance, which by the way is a negative log of the transmittance, okay? And then the next one here, remember these test solutions are at equilibrium. And so what we're going to try to do is try to get the actual molarity, okay, of the product, the iron thiocyanate ion or complex ion. This is 0.237. Here comes test solution 8, different concentrations, and that's going to be 0.376. And you can see in the video they're actually getting darker, so it makes sense that the absorbance is increasing. There's more of the chemical absorbing that set wavelength of light. Okay, so this is test solution 9. At some point we get 0.515 absorbance. And then, of course, the final test solution here. All right. And that's going to have the greatest molarity of my product, which is the colored iron thiocyanate, complex ion. So there was my 5 test solutions, and we're going to use those values to actually solve, knowing that the y is the absorbance, and knowing that my x is the concentration that I want to solve for, and knowing that I have y equals mx plus p, and this is giving me the slope and the y-intercept, I can actually solve for that. All right. So let's begin reviewing how we complete this Flynn lab, which by the way I think is one of the better labs they produce, and of course they're using the very, very infamous iron thiocyanate equilibrium reaction that is very common in many textbooks and essentially easy to deal with in the laboratory, even a high school science laboratory like mine. So in any case, we've got this equilibrium. What's nice to understand here is that the blood red color that we calibrated our spectrophotometer with at the 455 or so peak absorbance is, lets us understand that the red part of the spectrum is what we see because it's taking in a lot of the shorter wavelengths. But in any case, so the color that we're basically measuring is the blood red color here that was in the cuvettes that were mixed separately in test tubes and filled into the cuvettes for the reading. And essentially, using the color here, we're going to be able to determine the concentration, the molarity of this, by using the Beer's law graph that we've already gone through. So let's talk about the reference solutions to understand, of course, the objectives in this lab, which again is essentially the Flynn lab. I have adapted it, okay, for my students a little bit, but it's the same lab. Number one, the objectives are to determine the complex ions concentration by spectrophotometry, to plot a Beer's law graph with reference solutions that we know the molarity of the colored compound and get an absorbance for, and then 3, to calculate the equilibrium constant for this complex ion equilibrium reaction. So let's begin with talking about the reference solutions here. These reference solutions, okay, are put together for a particular reason that you must understand. And let's talk about the fact that we have an iron nitrate solution, which is delivering the iron plus 3 ion, okay? And then we have the potassium thiocyanate solution. Potassium is going to be a spectator. It's going to, as we know, group 1 ions are always soluble, as are nitrates. So the nitrate here is going to deliver the iron plus 3, and the potassium is going to deliver the thiocyanate ion, okay, which is negative. And they're going to come together and make our complex ion. Iron thiocyanate here, and of course you get a plus 2 with this. Okay, so that's what we're doing here. And so what's going on here? Well, to make a reference solution, we want to know exactly how much of the product that's colored that we're going to measure from the spectrophotometer we're producing. So we want to use Le Châtelier's principle to drive it forward to know exactly its concentration. So we mix different amounts, but notice the concentration of the iron nitrate. It's 0.2. Look at the concentration of the potassium thiocyanate. That's 0.0002. Whoa! This concentration is 1,000 times more concentrated. Don't forget that these are 1-to-1 relationships. So we're going to have a heck of a lot more iron nitrate than this ion here. And what's that's going to do by Le Châtelier's principle, if you're going to have a lot more reactants of one, as you increase one of the reactants, the reaction is going to shift and become more spontaneous in the forward to relieve that stress and lower the iron. So essentially what we're doing by this concentration being so much bigger than this concentration, 1,000 times, okay, what we're going to do is we're going to drive this reaction essentially to completion. This is going to go to completion. So we're going to be able to figure out the concentration. See, we want to build a Beer's law graph that we can clearly understand, that we can build it so that we can know the molarity of this colored solution and then plot a curve. Now, the Beer's law, of course, graph is very simple in the idea that the absorbance, A, that's how much light is absorbed or goes missing in the detector, okay, is going to go up as the concentrations get more, concentrated. But we got to know the molarities. So we're going to tell the computer, as I've already done for you, tell the computer what those concentrations are and plot them. The computer's going to measure the absorbance, and we're going to write the concentrations, and we're going to get this linear line with a best fit. And we're going to use that to solve for the equilibrium values. But in order for me to use spectrophotometry, I've got to set up a reference graph, a Beer's law graph. So this is very important to understand. And it's important to understand that we're going to essentially get this concentration of this chemical by using this concentration. Whoa. Remember, this reaction is essentially going to completion due to Le Châtelier's principle. So as much of the thiocyanate ion I have, we're going to drive that to essentially 0. That's exactly how much we're going to make. Remember doing your equilibrium problems, this would be a minus x, and this would be a plus x, but this is not equilibrium. This is stoichiometry. We're driving this reaction forward, okay? So as much of the thiocyanate we use up is exactly how much we make. And since we're driving it to completion because of Le Châtelier's principle, this being 1,000 times, the concentration of the thiocyanate ion will be the concentration of the complex ion. So I can build the Beer's law graph. So that's what we're doing here. And so the problem is we're pouring solutions together. And when you do so, we're going to have to solve for the new molarity. So we're pouring this solution, it's 0.00002 with a 0.2, or more importantly, we're pouring it in with an 8 milliliter. So a 2 milliliter solution with this molarity is going to get diluted when the new volume is 10 milliliters, right? We're going to pour a 2 milliliter solution with an 8, we're going to get 10, and we're doing that, okay, all here, 6, 4, 5, 5, 4, 6. So you notice we're steadily increasing the amount of the limiting reagent here, okay? and we're steadily decreasing the iron nitrate, okay? So we're going to make it, it's going to get more concentrated as we go down, but we have to solve for this concentration with MV equals MV, okay? And that's what we're doing in the next graph. And I'm after, okay, the potassium thiocyanate solution, because that solution is going to give me the actual solution, because it's going to be driven to completion. Obviously, we need some iron to make this complex. We have so much more of the iron than necessary, but it's there to drive the reaction. So let's get to the other page to look at how we solve for the concentration of the thiocyanate, the iron thiocyanate. And voila, it magically appears, okay? And of course, I'm getting these tables right from the Flynn manual or the Flynn student lab, and I just doctored this up to make this a little more easily read by my students and used. Okay, so again, we are going to have this concentration of the colored solution, and we're going to solve for it using the potassium thiocyanate, which is going to get totally used up. And what I'm using here, party people, is I'm using MV equals MV. It's the dilution formula. I know people tend to use that for acid and base, but it's really the dilution formula. Here is the current molarity of the potassium thiocyanate. Here's the current volume of that solution. Remember, that's going to be and become this by driving it to completion by Le Châtelier's principle. And we're going to solve for the new what? Volume, and it's going to go down. So if you notice, 0.002, okay, becomes 0.0004. Okay, but as we talked about, we're going to steadily what? Increase the concentration. Okay, and so therefore the concentrations increase here. Okay, so now we definitely know by using Le Châtelier's principle, driving the reaction to completion, and by using the molarity of the potassium thiocyanate, now we know it's equal to the actual iron thiocyanate complex ion. Now we have a concentration that we know for certain, or that we can use to do what? Put in the spectrophotometer, which we did, and these are the absorbance values. And I could plot this by hand, or as you watched me, the computer plotted it for me. And now I have a reference graph that I can now solve for later in this lab to understand the what? The equilibrium amount of the complex ion. Okay, so it'll make more sense as we keep going. So in any case, the next thing that we did already is we took and made these test solutions. So these test solutions I made, and I put them in the cuvettes, and these were 6, 7, 8, 9, and 10. These are the last 5 you saw me put in the spectrophotometer. Okay, and if you look very carefully, all right, these have the same concentration of the iron nitrate, which is delivering the iron plus 3, and we're steadily increasing the potassium thiocyanate. Okay, so that of course is going to increase, but notice we're going to pour these solutions together, so yes, they're going to get diluted. Notice we added some water, okay, here to make it equal to 10 milliliters total, okay, so that the volume is the same. All right, any case, so what we're going to do is move on to the next table, and we're going to solve for the initial concentrations. So here's the next table by Flynn. I've added some comments here to help my students guide them through this, but so these are the test solutions. These are the solutions where we're actually going to let the reactions get to equilibrium. If you look very carefully, as we talked about, this is a 0.002, 0.002, so we're not driving the reaction to completion. It's going to get to equilibrium. And all we're doing is doing with different concentrations of the thiocyanate ion, remember, delivered by the potassium. If you remember, this was all 5 milliliters here. So again, I'm using MV equals MV here to solve for the new molarity, because it's going to get diluted. Why? Because we're essentially adding other volumes together. So in this case, we want both the iron plus 3 and the thiocyanate, because we're going to have to, at some point, use an ice table to solve, or at least come up with, the equilibrium values of these guys. These are not the equilibrium values. Remember, we have to solve for the third objective is to solve for the equilibrium constant. So we're going to need these concentrations at equilibrium. That's the E part of the ice table. So in any case, we need to know what their actual starting molarities are. Okay, when we pour solutions together, they're going to get diluted. So 5 milliliters, hey, if you pour it into a new volume that is now 10, of course it gets diluted in half, and that's why the 0.001 here. And I wrote that more time. I kept repeating that because in this entire group right here, the amount of the iron ion stays constant. In the thiocyanate ion delivered by the potassium, okay, we do what? We steadily increase the amount. So we're going to change the concentration. So we have different test solutions. The reason why they're test solutions, we're going to see if our equilibrium changes if we have different amounts of the thiocyanate, ion compared to the steady. So it's a kind of like, a lab within a lab. But yes, we're trying to find the equilibrium constant. I'm going to see if it changes there. In any case, notice when I ran it through the spectrophotometer, these were the tests. This is not part of the Beer's law. These are the actual absorbance. Absorbance of what? Absorbance of the product. Okay? And that's going to give us a value at equilibrium. So we need to use the absorbance to get, very importantly, the product, the actual colored compound, the complex ion. And we need the starting molarities, and that's what we have here. So if you can understand, here comes the ice table. Okay? So what are we trying to do? And this is the part that people get lost in the sauce here. Okay, so let's not try to do that. So we're trying to figure out the equilibrium amount in these test solutions of these ions. And we're going to get the product's equilibrium molarity by spectrophotometry, by using the absorbance that we have done up here. Okay? Now think with me for a second. I know some of you might be not used to the ice tables. This might be a new part. But if you think with me for a second, we're going to start with 100% of our reactants. We always do that in ice table. You have 0 products. We always start that way theoretically. How far is this going to move forward until it reaches equilibrium? Well, it depends upon its equilibrium constant, right? How far does it go? And of course, we're assuming temperature staying constant because equilibrium constants are what? Temperature sensitive. So, to know these values here, we're going to get the actual molarity of the product, because the product has the color, okay, by using the Beer's law graph, and we're going to come up with this molarity. Now, because we're starting with 0 of the product, when we first start pouring these together, okay, after they're diluted, this is going to be plus whatever this number is. So that's your X. This value is your X. Where did this molarity come from? It came from the loss from these guys. So whatever this number is, that's going to be your minus X, and your plus X. So we're going to take, my friends, the initial concentrations of these values, and I didn't do all of them because I think you get the point. We're going to plug them in here. We're going to use the value from our Beer's law graph to determine this value, which is what's plus X or which is minus X. It's the value of X that's changing. And then we're going to subtract that to get the equilibrium reactants. And then we can plug it into the equilibrium expression and solve for KQ. This other table, again given by Flynn, okay, is going to help us get the equilibrium. This is going to be from the graph that we built from the spectrophotometer. And these values are going to be what? The equilibrium values after we subtract how much we lost, which is exactly what we gain, which we're going to get from the graph. And then we're going to plug them in to the equilibrium constant. So let me do one for you and model that. Not usually a good model, but I'll try my best. So we have 0.01, and we have 0.0002. Okay, those are our what? Initial. So I'm going to kind of clean this up a little bit because I've been circling and going crazy. So I'm going to put this in here. We'll put it in as red maybe. Okay, if you have Another color you want? Give me a shout out. No, no need to. Okay, we're going to go with the red. So we have initial, okay, we'll make that 0.001. I'm not going to make it. That's the molarity that we just found here for all of the irons. And then we're going to do the first test solution, which is 0.0002. Okay, so 0.0002. My short-term memory is going at this height. Yeah, 3 zeros. I can do this. Okay. All right. And we always start in equilibrium with nothing happening yet. Okay, we always started with all the way to the reactant to see how far it goes. To solve for what these are, I'm going to need to know how far this goes forward. And it goes as forward as how much of the complex is made. So now I'm going to go and go to the graph. Okay, and I'm going to try to find what the actual molarity is for this. Remember, this is test 6. And remember, our absorbance that we got from the spectrophotometer for test 6 is 0.116. So I'm going to go to the graph, and I'm going to use linear algebra and the Beer's law graph to come up with the molarity. Okay, so our absorbance for the test group or test Cuvette 6, number 6, was 0.116. Now, how do we use this? Very simple. Okay, we have y equals mx plus b. That's our linear relationship between concentration and what? And absorbance. As the solution gets darker, it absorbs more light. That makes sense. And we're taking our linear relationship here. Now we know that the y is the absorbance. So I'm going to plug that in as 0.116. I can do this, maybe not. So 0.116. And then we have the slope given to us in our best fit line to be M4075. And then the x, of course, is the molarity that we're trying to solve. That would be the molarity of the colored compound that we need that was produced at equilibrium. Okay, and then of course we have plus, in this case, minus, okay, 0.1162. That's the y-intercept. So the y-intercept is my b, and my slope is here, and I'm going to solve for m down here. So in any case, let's just do some algebra and figure this out. All right, and our molarity, or concentration, using the Beer's law graph and the reference solutions, for an absorbance of 0.116 for the test group, or the test 6, is 5.7 times 10 to the negative 5. That is the actual concentration, based upon our curve here, of the product of the colored compound, the complex. And we're going to need that. That came from 0, so that's your x, your plus x and your minus x in your equilibrium table. So let's get back there. Okay, so we just realized that, of course, we just found, our x, or the molarity of our test solution using the absorbance from the graph. And now we know that that is exactly the minus x and the plus x. And you've seen these in problems before. So now to solve, party people, what the equilibrium values are for these ions, you've got to subtract the x away. So in your handy-dandy calculators, 0.001 minus, in this case, 5.7 to the negative 5 here. And what I get is a value to be 9.4 times 10 to the negative 4. That is my equilibrium concentration. And I do the same for the thiocyanate ion, which is now 0.0002 minus the 5.7 to the negative 5. And that's going to be 1.43 times 10 to the negative 4. And of course, we have this value at equilibrium. We got that directly from the color that resulted when we poured these together when it reached equilibrium pretty quickly. And that, of course, is the 5.7 times 10 to the negative 5. And now, how do we get equilibrium? Well, equilibrium, okay, well, that's products over reactants. Okay, so the expression is going to be, okay, the Fe the products concentration over the reactants concentration, right? And because there's two reactants, we have these two here. And there's no coefficients. So as I always say in class, products over reactants, coefficients become exponents, and solids and liquids do not apply. So that is my equilibrium expression, which is nothing more than a formula that helps me decide who's favored when we reach equilibrium. So let's plug that in, okay, using that formula. All right, so we had the 5.7. Let's do that in the right color that we had it. So we're going to go 5.7 times 10 to negative 5. And that, of course, is my product over the concentrations. You can put the brackets there. And we're going to do Fe plus 2 was 9.4 times 10 to the negative 4. And thiocyanate ion, I was thinking cyanide, is 1.43 times 10 to the negative 4. And all we're going to do now is go find that KQ. All right. So I'm just going to plug this into my handy-dandy calculator. And I'm just going to solve for it. All right, 5.7 to e to the negative 5. Divide by the product of those two numbers, 9.4. And you can see how this is done. Not a big deal. And I hope you're connecting with your ice tables. That's why I like this lab. Okay. Times 1.43. And negative 4, close my parentheses. Okay, so what I get is I get 424. Equilibrium values do not have units. These, of course, are all molarity, as that's what you're going to use in an equilibrium table or partial pressures only. Okay, so I get 424 if my math is correct. Okay, and we're going to see how that number changes. Okay, it's an experiment as we change this concentration, because this is going to stay constant, the iron plus 3. Okay. Because it's going to be 0.001 for all 5 tests. This is going to change. And so you're going to do the same thing now. Remember, you're going to have to do the y equals mx plus b to find these concentrations, which is the new x, right? All right, and that's how you figure out the KQ. But now I'm going to continue on, all right, and do a little bit further. I've added some questions here. Now I want you to calculate the average value, okay, for the KQ here, all right. And then we're going to move on to the other questions that I want to explain. So what I would like to do now is go over my conclusion questions for this lab. In the first part of these conclusion questions, we're going to revisit the spectrophotometer, and I'm going to put the test solution number 10 back into the spectrophotometer. I'm going to show you that, and we're going to see how the absorbance changes if I have it soaking in an ice bath for a few minutes. So if you notice to the right, I have written already the room temperature absorbance that I obtained. Now, if we were doing this lab and you were able to heat the cuvette, you'd put this in. But if you didn't get a chance to do that in lab this year, just write in my 0.622 and please put in the absorbance in the ice bath that I get, that I'll show you in a couple of minutes here. And the purpose of this is understanding that equilibrium constants that we're solving for in this lab, it's one of the objectives, are sensitive to temperature. And we know that an equilibrium constant is very simply equal to in this case, the concentration of the products over the concentration of the reactants to their stoichiometric coefficients, meaning coefficients become exponents. Solids and liquids do not apply when we write this expression. Very generally, we think of the equilibrium value is equaling the products over the reactants. Okay, now, if we look at the absorbance, what we're thinking about here is the equilibrium that's in our cuvettes and our test solutions, are they getting darker or lighter? When I say equilibrium, we understand that the ion here, the complex ion, has that color, okay, that we're actually testing for in our spectrophotometer. So when we drop the cuvette, or at least sit in the ice bath, is the color getting darker or lighter? And the spectrophotometer, of course, will read that. If there's going to be a more pronounced color change in terms of there's more of the iron thiocyanate, which means it's going to get darker in color, we know that there's going to be a shift that is going to favor more of the products. And that would mean at that decreased temperature, if that is the case, the equilibrium constant is going to increase. And the question I'm asking here is the forward reaction endo or exo, or exothermic? And we always understand that an increase in temperature always favors the endothermic pathway, and a decrease in temperature always favors the exothermic pathway. So we're going to be able to understand whether it's exothermic or endothermic by looking at this part of this lab or the demonstration. Obviously, if the cuvette gets lighter in the ice bath, we're going to favor more of the reactants, and the equilibrium is going to adjust to favor more of the reactants, and that would mean in this case we're going to increase the amount of reactants for that new temperature compared to the products, and therefore your equilibrium value will decrease, all right, because you'll have more, or in this case, a larger amount of reactants or a bigger denominator. So that's what we're doing here, and so let's get back to the spectrophotometer, and I'm going to put in my test solution number 10, and we're going to now see what happens to that absorbance when I put that into the spectrophotometer and be able to understand if the forward reaction is exothermic or endothermic and what's happening to the equilibrium constant there. So let's do that. So we have our test 10 sitting in our ice bath, and I'm going to take it out, and we're applying a stress, and of course equilibrium is temperature sensitive, so it's going to create a new position of equilibrium, which the color is going to either be darker or lighter. Probably a giveaway now that you can see that's next to the others here. I'm just going to give it a good dry off here because I have it in a, don't want to put it in the spectrophotometer and have any water residue, especially getting in the way there. So now I'm going to put this in. All right, my spectrophotometer, make sure I have the ridges on the right side. Okay, and now I'm going to read the absorbance. 0.611 was what I had at room temperature, and now you can see it's 0.862. And actually, as it warms up, it's dropping. As temperature increases, the absorbance going down. But when it was colder, the absorbance went up. So this is telling you something about how equilibrium is shifting. So in the spectrophotometer, it is clearly warming up and going down. So our observations from the spectrophotometer show that when we had the cuvette, of course, in the ice bath, the temperature was, of course, lower. And from our room temperature value of 0.622 that I used for this lab, we were 0.8. So it definitely had a larger absorbance at a colder temperature. So that should be able for you to understand. So from your observations from what we just saw with the spectrophotometer and putting in a cuvette from our test solution number 10. Of course, that's mine, and of course, you may have done this in your lab, or in the case that you didn't, you can use the video here to fill in your conclusion questions. And so in the lab, when I ran the test solution at room temperature, I got absorbance of 0.622. In the ice bath, it was well over 0.8 something, and therefore there was an increase of absorbance at lower temperature. The absorbance, of course, is directly proportionate to the concentration of our product, which is responsible for the color. So you can, from that, understand and have enough information now if this forward reaction is exothermic or endothermic. We also observed that as the cuvette was warming, the absorbance was dropping. And both of those observations support, the same change in the equilibrium constant or shift to this equilibrium that both support whether the forward reaction is endo or exo. So that piece of information, both support that. So we can go on and do number 20. As we move on, you're going to write your mean equilibrium for the 5 test solutions that you should have done. And based upon the value of delta, based on the value positive or negative and the size, of course, of that positive and negative for your equilibrium constants, you should be able to tell me, does this support your observations or color changes, especially, of course, from what we just did. And number 22, I want you to calculate the delta G of the forward reaction using an equation that we have worked with previously. And of course, that's going to be delta G 0 is equal to negative RT natural log of K. So with your value of K, that is your mean, I want you to solve for your standard Gibbs free energy there. All right. And so that also should support our understanding. If your delta G is positive, that would mean that we're going to favor more of the reactants, and we should really have a equilibrium that's below 1. If our equilibrium constant is large and we're favoring more of the products, therefore the forward reaction should be more spontaneous and delta G should be negative. So all those things are coming into play here. Number 23 is a question that kind of reviews some parts of this that sometimes we don't touch on in spectrophotometry experiments. So what I want to do here is want to explain how we're going to solve for the absorptivity constant. The formula used to show that absorbance, which is the measurement of the missing light or wavelengths of light that the chemical, in this case the product, absorbed, is equal to the absorptivity constant times the path length times the concentration. Of course, that's the molarity. Now, B is the path length, and the length that the light has to travel through the cuvette is 1 centimeter. So you can treat that as 1. And the absorbance is what we read, of course, in the spectrophotometer for each cuvette that was placed, and this is the concentration. So we can see that if the absorbance is greater, so is the concentration. And that's the Beer's law type of relationship that we used for this lab. Now, how do we solve for this? Well, for your reference solutions, I'm asking you to do this. Okay, so we're going to do this 5 times. You're going to plug in your known molarity, okay, and this, of course, will be a 1, and you're going to, of course, use the absorbance that you wrote down earlier, and you're going to solve through algebra, okay, the value of the absorptivity constant for those 5 reference solutions. Now, that should stay the same, okay, and by the way, if you have the absorptivity constant, okay, already from your spectrophotometer, theoretically, as long as you have the absorbance, you can solve for this C, so we can actually use this. But in any case, I want to look at, for the 5 test solutions, I want you to solve for the 5 constants. And I want to see if they stay constant. And I want to, in 24, see where there's the greatest deviation. So what concentrations gave us the greatest deviation? And that kind of speaks to the limitations of the spectrophotometer. The spectrophotometer is trying to measure the light that was missing that came from the source to the detector, and if it's missing, it's because the chemical, of course, is absorbing it, okay, in crystal field splitting. But there's a limitation, okay, at actually both ends. And we'll see if your data supports that. So what possible limitations does a spectrophotometer have? And see what we have there and do your best to answer that question. All right. So in any case, hope you got something from this at some point, and I'll see you next time.